All right, everybody, let's work some thermo problems. Now, I have just a few, so I'd like for you to take a look at them on the screen, pause your video, try to work them out first, and then we'll work them out together. All right, so let's take a look at our first problem. In this one, we have, it looks like 3 moles of nitrogen gas here that's hot. We can tell that because the speed distribution is farther to the right. And over here we only have 1 mole of nitrogen that must be cold because it's shifted to the left on our speed distribution. Now, you can tell that there are fewer atoms in this speed distribution because there's less area underneath, because this is the number of molecules here. So this area over here should be twice as big as the area here. All right? Now, they're put in thermal contact, heat flows between the two, and so what's going to happen? Well, let's see. This one over here that's hot, it should shift to the left. And this one over here that's on the left should shift to the right. The thing is that this blue one is going to shift down and to the right because it's going to be spread out over more speed distribution. So it should end up looking something more like this, farther to the right. And then the yellow one should shift to the left and should look something more like this at the end. That's kind of crappy, so let me redraw them. Let me redraw this one. It should look more like this over here. Okay? So it's shifted up and to the left, and this one should shift down and to the right. But the key thing is that they should have the same average temperature. Oops. So the key thing is they should have the same final temperature, so the same final speed distribution. In our second problem, we have a gas that begins at X and goes around a cycle around this process. And they tell us that this one here is adiabatic. So remember that adiabatic means that Q equals 0 for that process, for the adiabatic process. All right? First temperature question is to rank the temperatures of the gases. We know that Y has to be the highest temperature. Ty has to be the greatest because it has the highest pressure times volume. And we know that X and Z are less than it, but how do X and Z relate? Well, adiabatic, remember, is steeper than a isotherm. So let me draw a couple of isotherms in here, some hyperbolas. So we have a colder hyperbola here and a hotter hyperbola here, and we're moving from the lower one to the higher one. And so that means temperature X must be greater than temperature Z. All right. Now, part 2 says, in which process does the internal energy of the gas decrease? Well, so that was 1. Here's 2. So remember that internal energy is 3/2 nR delta T. So delta U is proportional to delta T. So we're looking for where the temperature increases. That's going to be our increase in internal energy. So let's see, from X to Y, well, that'll work. So process number 1, the internal energy goes up. And then let's see, Y to Z, nope, that won't work, that's going down. And then from Z to X, we said Z is a lower temperature than X. So process number 3, in these two right here, we have an increase in temperature, therefore an increase in internal energy. Now let's look at our last part of the question. It says, in which process does heat enter the gas? All right, well, let's organize this. So here's question number 3. Actually, I should just do this. Let's see. For process number 1, delta U equals Q plus W. So let's see. For process 1, we have a positive increase in temperature, therefore internal energy. And the work is to the right, so that's negative. So heat must go in, so that a big positive plus this negative equals a positive over here. So this one will work. How about process number 2? Delta U equals Q plus W. And we have a negative change in temperature, so therefore a negative change in internal energy. We have no work done because it's vertical It's an isochoric or isovolumetric process, and so therefore heat must be negative for this number to equal that number. So that one won't work. How about process number 3? In process number 3, delta U equals Q plus W, and we have an increase in temperature, so that's positive. We're going to the left, so that's positive work. So what do? Well, they've given us a little extra information that helps us out. So we didn't actually have to do any of this. It's adiabatic, so the heat is 0. So this number, the work, must equal the internal energy, and the heat is 0. So for question number 3, the only process for which heat enters the gas will be process number 1. Question number 3, we have 3 moles of a gas. Stop right there. That means N equals 3 that are taken through the process from 1 to 2. Question A, calculate the total work done through the entire process. Well, the work over here is 0. So all I have to do is find this area right here, and that's the work there. Because remember that work equals negative P delta V, which equals the area. And for us, the area equals this area. So be careful. This is an easy mistake to make. I made it the first time I worked this out, actually. This is delta V of negative 2 V naught. So we have a pressure of P naught and right here a change in volume of negative 2 V naught for a grand total of, oops, there's negative out front, almost messed up again, positive P naught V naught times 2. Part 2, calculate the change in temperature of the gas in process 1 only. So that's from here to here. So, well, remember PV equals nRT, and so change in temperature would just equal PV over nR, whatever the delta is for that. And notice the pressure is not changing, and the number of moles won't be changing, and the universal gas constant will never change. So we end up with P over nR times delta V, which would be V final minus V initial. So that would be P naught over nR. Our final is V naught, and our initial is minus 3 V naught. So we end up with negative 2 P naught V naught over nR. All right, now they did give us the number of moles up here, N equals 3. So N equals 3, you can plug that in if you want. I'm just going to leave it as N for this particular problem. Okay, part C says calculate the change in internal energy of the gas for process 2. All right, so change in internal energy is 3/2 nRT delta T. And this one is for process 2, so we're going from here to here. Now, right here, this initial temperature right here is 3 P naught V naught, and the final temperature here is also 3 P naught V naught. So actually what we have in this problem is that the change in temperature for process 2 equals the negative of the change in temperature of process 1. So I can put that to use if I'd like. I can just put this in here as a positive. So I get delta U equals 3/2 nR positive 2 P naught V naught over nR. And some stuff cancels out. The N and the R cancel out. This 2 cancels out. And I'm left with a positive 3 P naught V naught. And that's our change in internal energy for the gas for process 2. All right, part D, the last part, says, does heat flow into or out of the gas for the entire process? Well, let's find out. Let's see. For the entire process, that's delta U equals Q plus W. And again, we start and end at the same exact temperature. So for the entire process, from 1 and 2, there's no temperature change, so that's 0. Okay, so no temperature change, so the internal energy change is 0. So 0 equals Q plus W. And we know that we have positive work here and work equals 0 here. So we have positive work done and Q equals negative the work, but the work is positive, so Q is negative for the entire process. Oops. There we go. Okay, problem 4. We have 4 moles of a gas, that's N equals 4 moles. Contained in a cylinder. Here's our cylinder over here with a movable piston. The gas begins at state A and is taken around a cycle back to state A. All right. So the first one, it says describe each leg of the process shown in the PV diagram. All right. So this is a curved process, AB. And so it looks like it's either going to be isothermal or adiabatic. How do we know? How do we know the difference? So here we have a PV value of, that's 1 times 400. So that's 400. And here we have a PV value of 5 times, what is that? That looks to be about a little bit past 75. It's going to go with 80. And so 5 times 80, hey, look at that. That's 400. So this must be an isothermal if that's 80 down there. Same temperature all the way across. So isothermal. All right. Now, this process is up and down with no work, so that's constant volume or an isovolumetric process. C to A is constant pressure, so that's isobaric. Okay, there we go. Part B. It says calculate the temperature at A. So right here at A, what's the temperature? So let's work that one up here. That's PV equals nRT, or T equals PV over nR. And we just plug in our values here. Now be very careful, everybody. I'm going to highlight this for you. This volume down here, this is pretty common. It's times 10 to the negative third, and this pressure is times 10 to the fifth. So please watch out. You'll get screwed over every time on the test if you don't pay attention to your units on the axis. So the temperature is going to be, what's our pressure here? 100,000 pascals times a volume of, let's see, negative 3, 1, 2, 3. So that's 0.4. 0.4 meters cubed divided by N, which is 4 moles, and 8.314 joules per mole Kelvin. And that, my friends, gives us approximately 1200 Kelvin when we multiply it out. Part C, how much weight must be placed on the piston to compress the gas in process A to B? All right, so we have this piston here like this, and it's up here at this volume, but then it gets compressed down to 1/5 of its original. So a mass must have been put on here or something to compress it. So this is just a forces problem. We have this piston, and there is an mg down. There is a force up, and that force is the pressure from the gas times the area. And we have a force down from the atmosphere on the outside. So that's the pressure from the atmosphere times its area. So what we end up with is mg plus the pressure of the atmosphere times the area must equal the pressure of the gas times its area. And that gives us mass equals the pressure of the gas minus the pressure of the atmosphere times the area divided by G. And if you put all these numbers in here, you will get a mass of about 163 kilograms if we use 9.8 for G. Part D asks for the change in internal energy of the gas for process BC. So change in internal energy is 3/2 nR delta T, or 3/2 N, number of molecules, Boltzmann's constant, times the change in T. So for us, we have number of moles, so we're going to use this one. All right, so that's 3/2 N, or 4 moles, times 8.314 joule per mole Kelvin. and our change in temperature. We have to find our change in temperature. Okay, so let's be smart about this from B to C. We know, we've just calculated the temperature right here. The temperature right here is 1200 Kelvin. This is an isotherm. This is 1200 Kelvin here. And then we reduce the pressure from 500,000 to 100,000. So remember that pressure is proportional to the temperature. We're keeping the volume the same. So if the pressure gets cut to 1/5, the temperature will get cut to 1/5. So that means this temperature here at the end will only be 240 Kelvin. So that's going to give us a temperature change of 240 Kelvin, the final, minus the initial of 1200. So we're going down in temperature. So 240 minus 1200 gives us 960 Kelvin negative. So I can put that over here as my change in temperature, negative 960 Kelvin. And when we work out all of this math here, we end up with negative 4,800 joules, approximately. Part E asks, calculate the work for the process CA. So that would be this from C to A. Hey, so that's just going to be this area underneath here. Or if you prefer, work equals negative P delta V. So we're moving to the right, so that's going to be negative work. So I can just find this area and then make it negative. So that's 100,000 pascals times a change in area of, 0.4, I almost made the mistake, of 0.08 meters cubed. And that gives us a negative 32,000 joules of work done. And part F says, calculate the heat for process CA. All right, so delta U equals Q plus W. So Q would equal delta U minus work. Now we just found out what the work was, so we can plug that in. This number here is going to be the negative of this, so that's going to be positive 32,000. But delta U we can find out doing this process up here again. And I've done that one already, so I'm not going to redo that whole process here. What we end up with is actually the positive of this value, because we're going back to the same temperature that we started off at. So it ends up being 4,800 joules of change in internal energy, and it's positive, minus negative 32,000 joules here, for a grand total of 80,000 joules. Voila, we're done.